Okay, I wrote down what time the lecture ends so that I know to stop rather than keep you longer than the 75 or 72 minutes or whatever. So anyway, it's me again. Any questions about anything before we start? Annie? Oh, yeah, I haven't decided yet. Question is, what exactly will Prelim 2 cover? I'm still thinking about that. I'm not sure whether it's going to stop right before the DFT or sometime in the DFT, which is what we're talking about now. Any other questions? Questions? Oh, I forgot. I have to bring my chalk over. Hey. All right. So, anyway, remember what we did last time? We talked some more about the DTFT, and we kind of wrapped up that stuff. And I talked about windowing, designing low-pass filters using windowing and all the kind of mushy terminology associated with that, like the passband ripple, the stopband ripple, and all that. And we moved on. The end of class, moved on to the next batch of stuff, the DFT. And the DFT stands for discrete Fourier transform, but everybody just says DFT. And it's an important tool in lots of different applications, not just signals and systems, but data science, machine learning, whatever. You see it everywhere you look. Anyway, I want to emphasize that note, this is very important, all caps, I'll just put note in all caps this time. Our approach differs from the book's approach. So, I want to emphasize that because honestly I think it's easier to understand if you do it this way, the way I do it, rather than the way the book does it. It gets a lot less confusing, but anyway, that's just my opinion based on years of experience. You don't necessarily have to buy into that. All right, so anyway, the basic concept, the whole development hinges on the concept of an endpoint signal. So development hinges, I'm not writing well today, am I? Hinges on the concept of an endpoint signal. And what is an endpoint signal? X of n is one of these when x of n happens to be 0 when n is less than 0, and also when n is bigger than or equal to cap n. And cap n here is just some positive integer. Okay? And thus, for example, x, this is one thing about endpoint signals, x of n, once you know it's an endpoint signal, is specified completely by its values, by the n numbers, x of little n, where n runs between 0 and capital N minus 1. And I'm always going to write it 0 less than or equal to n less than cap n. Okay, so that's what an endpoint signal is. And last time I said that there's some cool things you can do with endpoint signals, like any linear combo of endpoint signals is another one, so the set of all endpoint signals is a vector space. And at the very end of class we were getting into this notion of cyclic shifting, which is another thing you could do to an endpoint signal to give you another one. So we introduced the k mod n notation. So that's how you read that expression. And I hope everyone understands what's going on with that. And here's the definition. If you're given an endpoint signal, x of n, and given some shift value n0, where n0 is between 0 and cap n, just like the n's are for x of n. The cyclic shift of x of n by n0 is the signal, is the endpoint signal. So this is something that you do to endpoint signals that gives you another endpoint signal, y of n. So y of n is going to be given by the following equation. Y of n is equal to, and remember, y of n is an endpoint signal. So what is y of n for n less than 0? 0, yes, exactly. What is y of n for n bigger than or equal to n? 0. But in between 0 and n, it's going to be this, x of n minus n0 mod n. So this is when 0 is less than or equal to n less than cap n, and 0 when n less than 0 or n bigger than or equal to cap n. That's the cyclic shift of x of n by n0. It's another endpoint signal. So cyclic shifting maps the set of all endpoint signals to the set of all endpoint signals. Now, there's a way to think about cyclic shifting. And I don't know if you guys, when you were kids, there were these video games around Pac-Man, and maybe actually that was even before you were kids. That's probably when your parents were kids. Who knows? But there's these video games where if you go out the right side of the screen, you come in the left side of the screen on the same level. That's like a cylindrical state space. Or if it's a torus, or a Möbius strip, you might go out top right and come in bottom left. You've seen those kind of, right? Right? Haven't you seen those? Even the people in the band haven't seen those? Just kidding, Eric, not you, just in general. Alex? I'm pretending Alex is in the back of the room filming this. Have you seen those video games? Yes, of course you have. Okay, so that's kind of what's going on here. Okay, so how to visualize cyclic shifting is essentially this. You take the values in x of n and you slide them to the right by n0, and the ones that slop out past capital N, you wrap those around and put them starting at time 0. So you sort of slide the values of x of n, I'll do an example in a second, to the right by n0, and the ones that go off the edge, quote unquote, go off the edge at cap n, reappear, they get wrapped around to start at time 0. Okay, so let's do an example. How about this? How about x of n is equal to, how about x of n is equal to n plus 1, when 0 is less than or equal to n is less than 5, and 0 otherwise. Okay. What kind of a signal is x of n? Yes, it's a 5-point signal. Is it a 7-point signal? This is important. Remember last time I said that if you have an n-point signal, that you can always think of that signal as being an m-point signal for any m bigger than n that just happens to be 0 over the last part of its time range. And people call that new way of thinking about the signal zero padding. One of the reasons they call it that is that when you're doing actual real-life applications, you do have a sequence of numbers and you pad them with zeros. And that could be in data science, it could be in DSP, whatever. But the way we think of it in this class, because of our definition of endpoint signal, thinking of that guy as a 7-point signal is just another way of looking at the same signal. And this will become relevant later on. You may think I'm emphasizing something unimportant. But anyway, so x of n is an endpoint signal. And suppose n0 equals, how about 3? Okay. Let's form y of n, the cyclic shift of x by n0 equals 3. So let's form that signal. And actually, I'm going to write out the name of it in words because that formula is slightly complicated. So y of n equals the cyclic shift of x of n by 3. All right. So how does this y of n arise? Let's do a stem plot for x of n. So what's a stem plot for x of n? At n equals 0, it's going to be 1, and it's going to be 2, 3, 4, 5. So this is at time 1, 2, 3, 4. Actually, wait. Yeah, that's right. Okay, so at time 5 and after, it's 0. And at times less than 0, it's also 0. Okay, so that's what x of n looks like. Stem plot-wise, what does y of n look like? What you do is you take this graph and you slide it by 3 to the right. So this little 1 goes and sits over 3. The 2 goes and sits over 4. So this is y of n, defined as above. Again, y of n has to be an endpoint signal. So it's 0 for time less than 0. And here's 1, 2, 3, 4, 5. And it's 0 at 6, 0 at 7, and so on. But what is it between, what is it over this range? And actually 0 at 5 as well. The 1 at time 0, so this is 1, 2, 3, 4, 5, slides over to b at 3. So this is 1. The 2 slides over to be at 4. So this is 1 and 2. And the other values, the 3 and the 4 and the 5, they slide out to the right, but they come in from the left. So you have 3, and then 4, and then 5. See how that works? Cyclic shifting. You shift x to the right, and the ones that slide off the end of the cliff slide back in on the left. So that's cyclic shift by n0. Okay? So that's something you could do with endpoint signals. Very good. All right, what's another thing you can do with endpoint signals? Cyclic, what I call circular convolution. This is what everyone calls a circular convolution. So this is cyclic shifting, this is circular convolution. All right, if you're given two endpoint signals, and I will name them suggestively. So given two endpoint signals, call them, say, h of n and x of n. Their endpoint circular convolution is the endpoint signal y of n given by the following formula. Okay. Y of n equals what? Well, what is it for n less than 0? Hint, hint, it's an endpoint signal, cap endpoint signal. Y of n is a cap endpoint signal. What is it for n less than 0? It's 0, yes. What is it for n bigger than or equal to cap n? Michelle? Yes, it's 0. Okay, so it's equal to 0 when n is less than 0 or n bigger than or equal to cap n. But in between, what is it equal to? I want you to guess. I want you to try to guess how the convolution formula comes out. So I'm just going to stand here until I hear someone give me a guess. And what you want to be thinking is, see, I'll put it over on the subliminal, no, I won't even put it up there. What does convolution of h of x look like if you're just doing straight up convolution? It's a sum, right? It's a sum from n equals, or k equals minus infinity to infinity of h of k, x of n minus k. So what do you think the endpoint circular convolution formula is on that critical range of times between 0 and cap n? What goes here? What goes here? Let's give you a chance to think about that. Maria. Okay, you're right. Well, the sum from what to what, though? Before we write anything down, the sum from what to what? Oh, what's the relevant range of times for endpoint signal? Yes, correct. It's the sum from, let's use m for our index of summation. M equals 0 to cap n minus 1 of, Maria, you finished up now because I know you had the answer. H of, you were going to say k, but I changed it to m on you. Sorry. Okay? H of m, right? X of what? Yes. N minus m mod cap n. There you go. That is circular convolution. And this is a rule of thumb for endpoint signals. You know, any operation you have on arbitrary signals, you have a corresponding thing on endpoint signals. But whenever you're taking things like something minus something, you have to mod by n to make sure the value is in between 0 and n minus 1. That's sort of what's going on there. Okay, and I'm not going to draw any pictures or give any intuition for this. I mean, I'm bad enough at giving intuition for regular old convolution, much less circular convolution. But I will give you some notation that we're going to use. Y of n equals this. H of n star with a circle around it to indicate circular convolution. Sub n, put that there to indicate that they're endpoint signals. That's endpoint circular convolution. X of n. Okay? So that's the notation we'll use for circular convolution. And notice that, let's just write out this sum without any mod signs in it. So just to test your understanding, reality check. Note that y of n equals, I can write that sum that has mod sign in it this way. The sum from m equals 0 to little n, h of m, x of n minus m, plus the sum from m equals little m plus 1 to cap n, h of m, x of cap n plus n minus m, for times between little n and in between 0 and cap n. What did I do there? I just took the n mod cap n and noted that when little m is between 0 and little n, n mod little m is going to be just plain old n minus m. N minus m mod n is just n minus m because this quantity in here is non-negative. But as soon as m passes little n in the index of summation, this guy becomes negative. And so you have to add an n to it to make for n minus little n mod cap n. Critique. Yeah, you'll only ever have to add one cap n to it because this is always going to be, no matter how big m is in here, this is never going to get below minus n. It's never going to get to minus n or lower. It's always going to be between minus n and 0 when it's negative. So you only ever have to add one cap n to it to get it in the interval 0 to cap n minus 1. Okay? All right, so that's just to test your understanding of the law notation. All right, so those are cool things you can do with endpoint signals. All right, and we'll come back to those as we go later on. Where did I had a piece of paper here that I wanted to look at this point. I had a checklist for today. Okay, here we go. All right, so now we're ready to define the endpoint DFT of an endpoint signal. So now we're ready to define the endpoint DFT. How does this work? If x of n is an endpoint signal, we know it has a DTFT. And sometimes I will just, when I'm talking about DTFTs versus DFTs, I will put an underline under the T in DTF, the first T, and DTFT to indicate that I emphasize that we're talking about the DTFT. It has a DTFT x hat of omega hat. And, okay, hang on. I've got an incoming call here. Just want to see who it is. It's the doctor's office. I hope they didn't find out that I knew somebody who, well, I'll figure it out after class. It has a DTFT x hat of omega, and the so-called analysis equation holds. That is to say, we have x hat of omega hat equals the sum from n equals minus infinity to infinity of x of n, e to the minus j n omega hat. But notice, because x of n is an endpoint signal, this is a finite sum. It only goes n equals 0 to n minus 1. X of n, e to the minus j n omega hat. Okay? So far, so good? So we have a DTFT for x of n. This equation holds. Now, we're used to looking at DTFTs on the interval minus pi to pi in the omega hat space. As it happens, when we do DFTs, we look on the interval 0 to 2 pi. That doesn't gain us or lose us any information because the DTFT is 2 pi periodic, and therefore it's this, any 2 pi interval is enough to determine it. So let's focus on interval 0 less than or equal to omega hat less than or equal to 2 pi. Okay. So we have a picture of x hat of omega hat on that interval. And what we do is we record the values of x hat of omega hat at cap n equally spaced frequency points. So record the values. So this is kind of like sampling x hat of omega hat. So record the values of x hat of omega hat at the cap n equally spaced omega hat points. What are they going to be? 0, 2 pi over cap n, 4 pi over cap n, all the way up through n minus 1 times 2 pi over cap n. So this is kind of like, quote unquote, sampling x hat of omega hat, the DTFT of x. It's recording a set of cap n values of the DTFT of x. When we do that, we get n numbers. N numbers that are in general complex. So from this, we get cap n numbers. Okay, a list of cap n numbers, an ordered list. And what are those numbers going to be? We're going to notate them x hat bracket k. Now, I want to warn you again here, the book notation differs slightly from mine. So the book calls this, the book uses just cap x of k instead of cap x hat of k. All right? X hat of k equals x hat parentheses k 2 pi over cap n. That's just the one of the values in that list. It's x hat of omega hat evaluated at omega hat equals k 2 pi over n. And this is going to be true for k between 0 and n minus 1 inclusive. Terminology. This list of n, cap n numbers, this ordered list, x hat 0, x hat of 1, blah, 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 up to x hat of n minus 1 of, in general, complex numbers is called, drum roll please, the endpoint DFT of the endpoint signal x of n. So that's the definition of the endpoint DFT. Okay, so let's pause and think about that for a second. That's a second. What do we got here? We've got an endpoint signal, and we've got n numbers. But an endpoint signal is specified completely by its values over the critical range 0 through n minus 1. So in some sense, what we've got here is we've got n numbers associated with the signal determining n numbers somewhere else in the DFT domain, so to speak. And it turns out that that's another way of looking at DFTs. Rather than looking at them as sampling in x hat of omega hat at equally spaced frequency points, you can just look at it as some math thing you do to n numbers. And I'll get back to that in a second. But now what we're going to do, I want to take that equation up there for x hat of omega hat and evaluate it at omega hat equals one of those values. So observe that we have x hat of cap k, or cap x hat of k equals what? It equals, let's look at this equation, x hat of omega hat evaluated at k 2 pi over n. So this is the sum from little n equals 0 to cap n minus 1 of x of n e to the minus j k 2 pi over n. j n k 2 pi over n. And that's for k running from 0 through cap n minus 1. This follows from the analysis equation above. For the DTFT pair, x and x hat and omega hat. Okay? All you do is you plug in omega hat equals k 2 pi over n to that rightmost equation, that rightmost sum on the board up there, and you get this. And so we call, I don't know what to call this, so I'm going to call this the D-analysis equation. Last semester I called it the D-anal equation to save chalk, but then I thought it looked too much like D-anal equation. Someone in class said, "Oh, it looks like the name of that mountain in Alaska that used to be called Mount Denali, whatever." But I decided to just go for D-analysis. Okay, this semester we're going to be clean D-analysis. Now it turns out, and you might have guessed by the fact that I've named this equation something like analysis, that there's a desynthesis equation that goes the other way, and sure enough there is. It turns out you can show pretty easily I don't want to go through the proof in class, that this equation is invertible. And specifically, we have that x of n equals 1 over cap n times the sum from k equals 0 to cap n minus 1 x hat of k e to the positive j n k 2 pi over n, and n here runs between 0 and cap n. So that's the equation that gives you x of n from its endpoint DFT. And so I'm just going to call this guy D synthesis. Okay? Fair enough? Fair enough? You really want to see a proof? No, I don't want to do it now. Forgive me. Okay. Maybe I'll write a handout. I even forget whether they prove it in the book. That's true. Okay, so that's a definition of the endpoint DFT, and you have these two equations. And we'll write this kind of thing sometimes. Sometimes we call x of n the quote-unquote inverse endpoint DFT of x hat of k, 0 less than equal k less than n. That comes up sometimes. And sometimes we write something like this. We write like x of n, 0 less than equal to the n less than cap n, with a double arrow, and write DFT over it, x hat of k, 0 less than equal to k less than cap n, to emphasize the bilateral, invertible, two-way, bijective, whatever relationship between signals, endpoint signals, and their endpoint DFTs. Okay. Now, like I said earlier, you don't have to think, we approach the endpoint DFT, and the book does as well, as sampling the DTFT of the endpoint signal, recording cap n values of it at equally spaced frequency points. But you can, because of these equations here, like nothing about these equations, D analysis and D synthesis, requires that x of n be a signal, that you think of as an actual signal. It's just x of n is like a list of numbers, x of 0 up through x of n minus 1. X hat of k is just a list of numbers, x hat of 0 up through x hat of n minus 1. So you can think of this, so comment, this is a comment, and this is for you data scientists and machine learning aficionados and whatever. That's another place where the DFT comes up. You can think of this, of the endpoint DFT relationship, as just a Linalge thing, quote unquote Linalge thing, a relationship between n numbers, the x of n numbers, the n, it's cap n of course, x of n values, and the cap n x hat of k values. And you might say, oh, well, he says Linalge, right? So maybe there's some way to do this in terms of a matrix. Sure enough, there is. And this isn't something I will ever hold your feet to the fire on, because theoretically, I don't think linear algebra is even a prereq for this class. But let me just put it up to ease my conscience. It turns out that if you put all the x guys in a vector and all the x hat guys in a vector, you get this. you get, here's a vector of x hats. Have I ever gotten on the soapbox about linear algebra versus like diffie-q? That personally, I think linear algebra, in some sense, in the modern era of engineering, in ECE, any of the engineerings, really, is more fundamental in a sense than diffie-q. Now you fit, okay, so back row Sam, you kind of disagree? Because, well, you've seen a lot more of the physics stuff, right, than a lot of these people have, so yeah, so sure, you know, if you're more on the physical side of ECE, then diffie-q is definitely important. But I still don't think even there that I would teach it before I teach linear algebra, because to me it's so much easier to understand differential equations if you understand linear algebra first. Okay? Now, you may not buy that. And those of you watching at home, if there are other family members who you can run this question by them. Okay? Do you think that learning differential equations is easier if you learn linear algebra first? Maybe we'll run a poll on that later on. But anyway, the vector of x hat values turns out to equal a matrix, I'm going to call it psi for whatever reason, times the vector of x values. Where psi is the n by n matrix. And we can't say the ij entry of psi because we're teaching an ECE class, right? Okay, so I and j mean something else. Whose pq entry is this. E to the, and you're going to have to believe me on this, I'm not going to prove it. It's e to the minus j, p minus 1, q minus 1, 2 pi over n. For 1 less than or equal to pq less than or equal to cap n. And look, notice, because we're talking about a matrix, we have to use MATLAB-y kind of indexing. We have to have things running from 1 to cap n instead of 0 through n minus 1. And what that leads to is awkward stuff like p minus 1 and q minus 1. Why can't we just settle on 0 being the beginning of everything? I don't know. Okay, so that's a linear algebra way of looking at the endpoint DFT. So now what? Once we define something, it's always good to do a few examples. Actually, that's a good time to take a 3-minute break, and maybe it'll just be a 2-minute break, so I can check the voicemail from the doctor's office and see what they have to say. Okay, nothing about coronavirus. Just, oh, do you want to come in and get your blood pressure checked, have a physical, you know, you're about due. You know, the last one I had was last June, so anyway. And unfortunately, my doctor of like 20 years plus decided to move away from like family practice, and now she's doing like ER work up at the convenient care center. But she was like the best doctor, honestly. I don't know what I'm going to do. I don't know the new people. We'll have to see. Okay. So let's do some examples. Now that we have the definition of the endpoint DFT, let's do a few examples. A few examples. First off, how about, well, dumb example, the zero signal. Hello? What is the endpoint DFT of the zero signal? It's the list of n zeros. Okay. You plug in x of n equals 0 into either that Lin-Alge equation there or that equation, that d-analysis equation up there, boom, you get zeros for the x hats of k. So that's pretty obvious. How about delta of n? How about x of n equals delta of n? What is the endpoint DFT of that signal? What I'm going to do is I'm going to do a couple of these I'm going to do two ways. Okay. First way is I'm going to figure out the DT FT of x first and then sample it. And the other way is I'm just going to plug the signal right into d-analysis. Forgot, new name, d-analysis. And figure out what x hat of k is. So x hat of n equals delta n. So let's do this two ways. And you may say, oh, this is so beating a dead horse. This is so boring. Why don't we do it just one way? Let's do it two ways. First way, method 1, find x hat of omega first, x hat of omega hat first, then sample it. Because x hat of k you get by sampling x hat of omega hat. What is the dTFT x hat of omega hat for x of n? It's just the constant function 1. That's one of the examples. That we did when we talked about DTFTs. So what does that mean? That means that, in particular, x hat of k 2 pi over n is equal to 1 for all possible k values, which means that x hat bracket k is always equal to 1 for all k in the range 0 plus equal k less than n. So this is the answer. This is the endpoint DFT of the delta. It's a list of capital N ones. Okay, so it's a list of ones. Method 2. Let's just plug it in. Let's plug delta of n into question. What's your name? Aditi. Yeah. Okay. That's a good question. Okay. All right. Let's back up a little bit. X of n is delta of n, right? We know that's a signal. That's 1 at time 0 and 0 everywhere else. The question is, aren't DFTs for endpoint signals, not arbitrary signals? And the answer is yes, they are for endpoint signals. But delta of n happens to be an endpoint signal for all n. Okay? Because it's a signal that is 0 for time less than 0 and 0 for time bigger than or equal to cap n. And it just happens to be 0 at all these other times in that critical interval, but that doesn't absolve it from being an endpoint signal. So yeah, that's a good point, that this is, note, this x of n is an endpoint signal for all cap n bigger than 0. So yeah, I'm glad you mentioned that actually. That's something I should have thought of before. Isn't this cool? Because I can think, oh, I should have said that, and then I could credit one of you guys with coming up with the idea of asking a question. How about that? All right, method 2. What was your name again? Aditi. Okay. Method 2. Plug x of n into, so x of n equals delta of n, into the equation D analysis. So what do we get? We get x hat of k equals the sum from little n equals 0 to cap n minus 1 of x of n e to the minus j n k 2 pi over n. 0 less than k less than n. And if I plug in a delta there, there's only one non-zero term in this sum, and that corresponds to little n equals 0. And the exponential when little n equals 0 is a 1. The delta when n equals 0 is a 1. All the rest of the terms are 0. So this is equal to 1 plus 0 plus dot 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 plus 0 for 0 less than k less than n. And we conclude again that x hat bracket k is equal to 1 for k between 0 and equals 1. All right, so there's your delta. Okay. Very good. Delta in the time domain goes with a list of ones in the DFT. How about a shifted delta? How about a shifted delta? Say delta of n minus n0. So x of n equals delta of n minus n0, where, say, cap n is given and n0 is between 0 and cap n. I need this to ensure that this is an endpoint signal, a cap endpoint signal. All right, so shifted delta. This one, I could do method 1, I could do method 2. I'm just going to do method 2 for this one. So just do method 2 above, plug it into D analysis equation, and what do you get? You get x hat of k equals the sum from n equals 0 to cap n minus 1 up. What is x of n? It's delta of n minus n0, e to the minus j nk 2 pi over n. And again, and of course this is always over the range, 0 less than k less than n. Again, we have only one non-zero term in the sum, and that term is the little n equals n0 term. So it becomes 0 plus dot 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 plus 0 plus e to the minus j n0 k 2 pi over n plus 0 plus 0. And we conclude that this is the case. Conclude that x hat of k is equal to e to the minus j n0 k 2 pi over n over that critical range 0 through n. So that's the endpoint DFT of the endpoint signal delta of n minus n0, shifted delta. All right. Am I going too fast? Too slow? Okay. How about this one? How about x of n equals 1 when n is between 0 and cap n, not including n, and 0 otherwise. Okay, so this is a list of ones in the time domain. We've already seen a list of ones in the DTFT domain. Let's do a list of ones in the time domain. And maybe we'll have some duality thing going on. Like maybe this will come out to be like a delta in the DFT domain. We'll see. We'll see. This one I am going to go through method 1 and method 2. One of the reasons I want to go through both is that method 2 illustrates a cool thing using partial geometric series that comes up a lot in DFT. So let's do method 1 first. First, you get DTFT, x hat over omega hat, and then sample. All right, now why is method 1 a good one to use based on our prior knowledge? Because we know what the DTFT of the signal is. It's one of our canonical examples. We have seen that x hat of omega hat is equal to Dirichlet thing, dn of omega hat, and we were using L before when we were talking about the pulse of length L, times e to the minus j n minus 1 over 2 omega hat. And what is dn of omega hat? Is equal to, that's equal to sine of n omega hat over 2 divided by sine of omega hat over 2. That's Dirichlet thing. All right. So that's our DTFT of the signal x of n. To get the endpoint DFT with no t, we sample that at the equally spaced intervals k2 pi over n. So thus, x hat bracket k equals x hat parentheses k2 pi over n equals, all I do is I plug k2 pi over n in there, and I get this. D cap n of k2 pi over n times e to the minus j n minus 1 over 2 k2 pi over n. And that's true for 0 less or equal to k less than n. Okay. Now, let's pause for a minute. This is correct. I wouldn't have written it up there if it weren't. But if you look carefully at it, you'll see that it simplifies radically. How so? So while this is correct, a closer look reveals that well, let's look at the Dirichlet thing. The Dirichlet thing has sine of n hat n omega hat over 2 in the numerator, right? So dn of k2 pi over n, that's going to be equal to sine, let's write this down, n omega hat over 2, so omega hat over 2 is k2 pi, or is k pi over n, so it's going to be sine of k pi, right? Or, yeah, over sine of k pi over n. That's what omega hat over 2 is, 2 pi over n. And this is equal to what? It's equal to 0 when k is bigger than 0. So it's equal to 0 when 1 is less than or equal to k less than cap n. Right? Sine of pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, those are all zeros. So all the values of x hat of k for positive, strictly positive values of k are 0. And the only possibly non-zero one is when k equals 0. And sure enough, by L'Hopital, and remember, always include the circumflex over the O in L'Hopital, and remember that circumflex over a vowel in French means that way back when, there was an S after it. So, L'Hopital, by L'Hopital, dn of 0, and we've calculated dn of 0 before, right, is n. So the bottom line is that x hat of k is equal to 1 when k equals 0, because that's dn of 0 times 1. Sorry, it's equal to n when k equals 0. And it's equal to 0 for the other values of k in the critical interval 1 through n. So, sure enough, back to my kind of warm-up to this example, like where we had a delta in the time domain, we had a sequence of 1s in the omega in the DFT domain. Here we've got a sequence of 1s in the time domain, and over the frequency domain, or omega DFT domain, we have a delta, essentially, and delta of 0, or delta of k, something like that. All right? Great. All right, method 2. Let's do method 2 here because method 2, like I said, illustrates a cool, well, cool to me. I think it's cool. You may not, but there's no accounting for taste. Manipulation involving partial geometric series. So let's do that. So let's use method 2. What is method 2 again? It's plug the numbers x of n from 0 through n minus 1 into the d-analysis equation directly. So plug x of n into d-analysis equation. And what do you get? You get x out of k equals the sum from n equals 0 to n minus 1, x of n, e to the minus jk to jnk. I always forget that n for some reason. In fact, that makes me want to look and make sure it's not missing in any of the other. No? I'm doing pretty good today with that. Yeah. So this is equal to the sum from n equals 0 to cap n minus 1 of e to the minus j n k 2 pi over n. And that's going to hold over the range 0 through n minus 1 in k space. All right? What is that equal to? Well, what I'm going to do is I'm going to manipulate that sum using partial geometric series. So note that x hat bracket k is the sum from little n equals 0 to cap n minus 1 of what? It's something to the n. It's e to the minus j k 2 pi over cap n to the little n. Right? The little nth term in that sum is this guy to the little n. And by partial geometric series, so this is by partial geometric series, we get that this is 1 minus, well, let's split it up. It's equal to n when the thing in parentheses, e to the minus j k 2 pi over n is equal to 1. And it's equal to 1 minus e to the minus jk 2 pi divided by 1 minus e to the minus jk 2 pi over n when that's not true. When not this. Now, if you think about it, what is this thing here? The bottom thing is 0 because e to the minus jk 2 pi is 1. And as it happens over the range, 0 through cap n minus 1. So over the range, 0 less than or equal to k less than cap n, e to the minus jk 2 pi over n equals 1, only when k equals 0. So what that means is that this guy x out of k is 1 when k equals 0, and meanwhile, for all k bigger than 0, in fact for any k, 1 minus e to the minus jk 2 pi is equal to 0. Conclusion, x out of k is equal to n when k equals 0, because that's when e to the minus jk 2 pi over n is 1, and it's equal to 0 when k is one of the rest of the values. And sure enough, that's the same answer we got using method 1, and it would be worrisome if it weren't. Okay? Are we good on that? Okay, let's step this one up a little bit. Oh, yep, that's right. How about next example is, and this is an important one, okay, x of n is equal to e to the j n omega 0 hat when n is between 0 and cap n and 0 otherwise. And here I'm going to assume omega 0 hat is some frequency between 0 and 2 pi. Okay, so this is like one of those truncated complex exponential sinusoids that we talked about last time. We found the DTFT of one of those, and it was like a Dirichlet thing, it had some phase to it, whatever. And as the length of the truncation extended to infinity, it got more and more sharp. And you remember that from last time, maybe. And if not, you can just scroll back and look at the lecture. Let's see what comes out of this one. Comes out with this one. And you could do method 1, you could do method 2. I'm just going to do method 1 for now. I'm going to find x hat of omega hat and sample. So let's apply method 1. Recall that, and this is something we actually did in class, even if it was of length cap L. X hat of omega hat, the DTFT of this guy, x of n, is going to be Dirichlet thing of, well, maybe, did we do it in class? Now I'm feeling a little guilty. Okay. Yeah, well, we're still going to apply method 1. Apply method 1. Okay. First recall, let's first find x hat of omega hat as follows. Recall that. Now this is one I know we did in class. That if I look at the pulse p of n, which is 1, when n is between 0 and cap n, and 0 otherwise. And we, of course, when we did in class, we used cap L, but we're using n here. That has dtft p hat of omega hat equals Dirichlet thing sub n of omega hat times e to the minus j n minus 1 over 2 omega. Okay. And actually, this is the same as the x of n we just talked about a minute ago, but I want to call it p of n in this problem because I don't want you to get confused with the x of n in this problem. This example. Because the x of n in this example is so since x of n is equal to e to the j n omega 0 hat times p of n, by the frequency shift rule for DTFTs, again, the TFTs, we have that x hat of omega hat is equal to p hat of omega hat minus omega 0 hat. And what we get when we do that is we get dn of omega hat minus omega 0 hat times e to the whatever it has to be. So it's e to the minus j n minus 1 over 2 omega hat minus omega 0 hat. So that's what x hat of omega hat looks like. It's like a Dirichlet thing centered on omega 0 hat with some phase. It's like a generalized linear phase thing. So parentheses, Dirichlet thing centered on omega 0 hat with some phase. Okay, that's how you can summarize that. You can tell your boss that that's what x hat of omega hat looks like, and she will not complain. Okay? All right. So you've got your Dirichlet thing centered on omega 0 hat. How do we find the DFT? Not TFT, but the DFT of x of n. We sample this every k2 pi over n. So then you get x hat of k, 0 less than k less than n, by sampling this thing, x hat of omega hat. And what comes up is this. X hat bracket k equals, all you do is you plug in k2 pi over n for omega hat. So dn of k2 pi over n minus omega 0 hat times phase. And that's going to be the value of x hat of k, and that formula holds for 0 through n minus 1 k space. All right. Now, if you want, this is the way I like to think of it. Like, this is a list of cap n numbers, so you can think of them as like a stem plot if you want. You can do like a stem plot. What is that stem plot going to look like? Where are you going to plot it? Well, let's plot x hat of k over the omega hat value to which it corresponds. So here's a way, not the only way, to think about this. Okay. Let's look at the interval 0 to 2 pi in omega hat space. So focus on the interval 0 less than or equal to omega hat less than or equal to 2 pi. And do a stem plot-ish kind of thing of x hat of k, where you plot x hat of k over k2 pi over n. So do a stem plot of x hat over k, where x hat of k appears, the x hat of k stem is at frequency omega hat equals k 2 pi over n. What's going to happen modulo the phase, and again, I'm sweeping the phase under the rug, and this room has a really kind of ugly wall-to-wall carpet, so it's not even a rug. It's hard to sweep stuff under it. Nope, no rips or anything. Sweeping the phase under the rug, so ignoring phase, just graphing, not the magnitude quite even, the Dirichlet part, I'll call it, you get something like this. So focusing on the interval 0 to 2 pi in omega hat space. So here's 0, and here's 2 pi. So you're going to get, and say omega 0 hat's out here, and let's divide omega hat, before I put in omega 0 hat, let's do it this way. Let's divide this up into, say, let's do it this way, half, quarter. So I'm doing this in 12s without even thinking about it. Okay. Let's make sure there's 1, 0, 1, 2, 12. Okay, so let's say cap n equals 12, right? So this is 2 pi over 12. This is like 2, 3, 4, 5. 10 pi over 12, 5 times 2 pi over 12, and so on, etc., right? Now, what happens? Say omega 0 hat is in here. How about it? So omega 0 hat, and say it's between, in this case, it's between pi over 2, which is this value, and pi over 2 plus 2 pi over 12. What's going to happen is you're going to have, like, your stems are going to be like so. They're going to be Dirichlet-ish, like, you know, something like this. I don't know. So, whatever. But, you know, like, and the same guy over here is going to be symmetric. Dirichlet cars, blah, 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 blah. And this is going to be here. It's going to be here. And so on. Whatever. Anyway, something like that. So it's going to look like the envelope, if you take your contacts out or your glasses off or whatever, it's going to be a Dirichlet thing whose, so this is here, this is 7 pi over 12, right? Or 7 times 2 pi over 12. It's going to be a Dirichlet kind of envelope, and the highest one is going to be at the K0 value, where K0, 2 pi over 12 is closest to omega 0 hat. So it's going to be a Dirichlet-ish. Maybe we should call it Dirichlet-esque because it sounds more French. I'm just going to call it a Dirichlet-ish bunch of stems. Not in general symmetric, because they're not right there on omega 0 hat. With the tallest one at frequency K0 2 pi over n, which is the closest to omega 0 hat of all the K2 pi over n's. Now, it turns out that this picture holds when omega 0 hat is not exactly equal to any of these guys. If it is, this is the last thing I'll say today. If omega 0 hat happens to be equal to K0 2 pi over n for some K0. So if, on the other hand, omega 0 hat exactly equals, say, K1 2 pi, just so you don't confuse it with the K0 up there, for some K1, we find that x hat of K is going to be a delta. It's going to equal cap n when k equals k1 and 0 when k is not equal to k1. And of course k is running over the range 0 to n as always. And I will wrap up this case next time, which we can do using either method 1 or method 2. So let's leave it at that for today. And again, I forgot to say this last lecture. I hope you're doing okay. I miss you guys a lot. And today was kind of a sunny day, at least for a while. So that was mood elevating. And spending all this time at home, projects and stuff, the gym's closed, so, I've been down in the basement and had the wet basement company come by today, and they're going to send me some god-awful estimate for what it's going to cost. Anyway, you don't want to know that. Well, maybe you do. We're all humans, right? Okay, so hang in there, and I'll see you next time. And now for the awkward moment where I end the video. How is this going to work? Last lecture I had a heck of a time figuring this out, but today it's going to stop now. No. Now.